Hello everyone. Today we are doing section 9.5, the cross product. That's a little bit away from the vectors which we did study like a week ago, right? Well, the reason is because I'm planning to use determinants and we just covered determinants to use them for this section. Okay, so we already know that with vectors we can multiply them by a scalar, by a number. Basically just stretch the vector or, well, make it shorter. We also can multiply two vectors as a dot product. Dot product is going to give us a number, right? And that's a scalar. Now, another way to multiply two vectors is called a cross product. By definition, cross product between two vectors, vector u with three components, and vector v with three components, v1, v2, v3, is going to be a determinant of matrix 3 by 3. So I'm going to write it down. First, we are going to put cross between vectors to not confuse it with dot, which was the dot product, right? And then I'm going to write down that it's a determinant of next matrix. On the top row, we are going to put basis vectors I, j, k. Second row is going to consist out of components of the first vector, u1, u2, and u3. And the last row is going to consist out of components of the second vector, v1, v2, and v3. And we calculate the determinant of this 3 by 3 matrix. And that's why we actually studied the determinants, right? And that's going to give us a cross product between two vectors. Let's do it. We remember that if we want to calculate the determinant of 3 by 3 matrix, we can expand it by the first row. So we take the first term of the first row and multiply it by the complementary matrix, right? Which is determinant of u2, u3, v2, v3, determinant of 2 by 2, right? Then goes minus, because we have sign alternation, plus, minus, plus. And then determinant of complementary matrix is going to be u1, v3, u1, v3 here, and u3 and v1 here. And then plus sign alternation and u1, u2, v1, v2, the matrix which is complementary to k. You cross out k, you are going to have leftover matrix of these four elements. Okay, now I'm going to write them down as like normal numbers, right? So it's going to be I, and here is going to be what? U v3 by u2 minus u3 by v2, right? Minus j u1 by v3 minus v1 by u3, and plus k u1 v2 minus u2 v1, right? Okay, you see that the result actually has component vectors I, j, and k, and can be represented as like a vector. So cross product is not a scalar like a dot product, it's a vector. And components of this vector, you don't need to memorize it. If you remember that it's a determinant, it's going to be easier always to write down the determinant instead of memorizing very complicated formula. Minus u1 v3 plus v1 u3 and u1 v2 minus u2 v1. Again, I do not suggest you to memorize the formula for cross product, but I suggest you to memorize that it's a determinant. And remember, how do we calculate determinants? Okay, now time to do an example, right? Remember my favorite vectors u and v. They are 1, 2, 3, and another one is going to be what? 4, 5, and 6. What is going to be the cross product between these two vectors? U cross product v is going to be I, j, k, right? And 1, 2, 3 here, and 4, 5, 6 over here, and determinant, right? Which is I, and determinant of this matrix is what? 2 by 6 minus 5 by 3 minus j, and determinant of leftover matrix is 1 by 6 minus 3 by 4, and plus k, which is going to be what? 1 by 2, 1 by 5 actually. Oh, sorry. Write down 2, 1 by 5, and 2 by 4, which is going to give us I multiplied by what? 12 minus 15 is negative 3 minus j And here we have 6 minus 12 minus 6 and plus k, which is going to be 5 minus 8, again minus 3. If we write it down in components form, we are going to have minus 3, 6 minus 3. You see that the result is a vector, not a scalar like a dot product. So, well, slightly different, right? But more math involved, but not that difficult to calculate, right? Interesting facts about the cross product. Let me put that over here. Interesting facts. Fact number 1. Remember that dot product was not sensitive whether you put v first or u first or switch them, because it's just a product of coordinates. Does not matter in which order you multiply them. Cross product is going to be sensitive to the switch of the vectors. So my first interesting fact is that cross product of vector u and v is going to be minus cross product of u and v and u. Why does it happen? Well, we already learned the determinants. We remember what happens in determinant when you switch the rows. Determinant changes a sign, and that's the reason why it's going to change the sign if you exchange the vectors. I'm going to write it down. So determinant changes the sign if we switch rows. Well, it's not necessarily rows, it can be columns, but in this case, we're switching the rows, right? Okay. Well, just remember about this. Makes sense to know which vector is first and which vector is second. Number 2, vector C, which is a result vector of cross product u and v. Well, this one, for example, here, vector C is minus 3, 6, minus 3, is going to be perpendicular to both u and v. Let me kind of write it down first and then explain why it's going to happen. So vector C, the result vector of cross product, is perpendicular to original vectors. C is perpendicular to both u and v. What I'm going to do, guys, I'm going to first check it with my vector, which I calculated, and then try to prove it. And if you don't understand my proof, believe me, because we checked it, okay? Okay, I'm going to first check it. So what I'm going to do, guys, I already have the cross product between vectors 1, 2, 3, and 4, 5, 6, right? That's minus 3, 6, and negative 3. Now, how do I check if they're perpendicular or not? Well, I'm going to calculate the dot product between them, right? Oh, sorry, instead of erasing, I just made it messy. So I'm going to calculate dot product between vector u and vector c, which is a resulting vector of cross product, right? My vector u is 1, 2, 3, dot product between minus 3, 6, minus 3, right? Well, we multiply x, that's 1 by negative 3, plus 2 by 6. Should not write down this dot over here. People will not understand it if they look at my notes. And plus 3 multiplied by negative 3. Now, let's multiply everything. It's minus 3 for the first one, right? Plus 12 for the second one, and minus 9 for the third, you see, equals to 0. So they are perpendicular. So C is perpendicular to U. Well, let's check if C is perpendicular to V. So again, my vector V is 4, 5, 6. And my vector C, the cross product between U and V, is minus 3, 6, minus 3. So it's 4 by minus 3 plus 5 by 6 plus 6 by minus 3. And I have minus 12 plus 30 and minus 18. Well, you see minus 12, minus 18 are making 30 with minus, and this 30 with plus, so it's 0 again. So cross product is perpendicular to vector V. Why does it happen, guys? Well, now it's time to probably give a little proof. But again, it happens because of the properties of the determinants. I'm going to move to next page because I don't have any space here to prove it, okay? And prove it. Prove. Okay, So let's consider two general vectors, vector u with components u1, u2, and u3, and vector v with components v1, v2, and v3. We remember that cross product between them is going to look like this: I, j, k, u1, u2, u3, v1, v2, v3, and the determinant, right? And again, I have lots of unnecessary dots around. So now I'm just going to expand it like I did in the beginning. u2, u3, v2, v3, minus j, u1, u3, v1, v3. A little bit long, but if you understand the proof, that's going to be very cool. u1, u2, sorry, it's supposed to be v, writing down u instead of v, v1, v2. Okay, so that's just, I'm just taking two arbitrary vectors and using the definition of cross product, right? Now, if this is going to be my resulting vector, right? So this is x component, y component, and z component. X component, y component of my resulting vector, and z component of my resulting vector, right? Now, if I want to find a dot product between this vector and, for example, vector u, how it's going to look? Well, let me label this vector c. If I want to find the dot product u and c, I'm going to have my c is a cross product already, so it's a dot product between the cross product. In math, we call it a triple product. Triple product. It's not necessary to memorize. You are going to learn it eventually. Okay, give me a second. This multiplication sign does not look like multiplication. Looks like a minus. Okay, so what are we going to have? Well, we'll take x component multiplied by x component of u. So we're going to have u1 multiplied by and then plus x component of my vector u, y component of my vector u, and y component of my vector. Remember, guys, that y component here is multiplied by minus, right? So I'm going to copy the matrix here, but I'm going to copy also the minus. I have to actually multiply u2 by minus determinant of this matrix. Well, if I just put minus in front, it's not going to change anything, right? I just don't want to put minus in front of this, but I want to put minus in front of the whole thing. I just taking minus outside, let's say. And the last one is u3 and z component, right? Which is u1, u2, v1, v2. Now, guys, if you look at this expression, you probably are going to see that this expression looks exactly the same way as this one, but this one is obtained from the determinant of the matrix, right? So this one is also determinant of some matrix, right? Which matrix? Well, it just, if we put instead of I, j, and k, u1, u2, and u3, we are going to have an interesting determinant, u1, u2, and u3, and copy the bottom, u1, u2, and u3, v1, v2, and v3. Imagine now that you expand this matrix by the first row determinant. How it's going to look? Well, you take u1 and multiply by the determinant of this matrix, right? And that's exactly what you have here. And then minus u2 and multiply by determinant of this matrix. And u3 and by determinant of this matrix. So basically, guys, we rolled it back into determinant of 3 by 3 matrix. But this 3 by 3 matrix has same rows. Row number 1 and row number 2 are same. You remember what happens to determinant if they are same. Determinant is equal to 0. So we proved our point that actually this vector u and vector c, the result of cross product between u and v, is going to be perpendicular to vector u. I'm not going to prove it for vector v, but it's just like going to write it down that same for v. So same for v multiplied by c, or v multiplied by u cross product v, still going to be 0. Now I'm going to draw the picture how it's going to look. So actually the resulting vector is perpendicular to both original vectors. geometrically is going to look like this. Geometrically. Imagine that this is vector u, and this is vector v. My vector c is supposed to be perpendicular to vector u and to vector v at the same time. So that's my cross product, u cross product v. It's perpendicular to both of them. So basically, it's going to be perpendicular to the whole plane, which is described by these two vectors, u and v. It's like, imagine that you have two crossing lines. You draw a plane through them, and vector c is going to be perpendicular to the whole plane. Well, guys, there is interesting rule which tells you how to choose the direction of vector c, because there are two perpendicular directions to a plane, right? Up or down, the right-hand rule. Right-hand rule is going to look like this. If you curl your fingers from the first vector to the second, from vector u to vector v, like this. Well, I'm not very good in drawing, but if you curl your finger, your thumb is going to show you direction of vector c, the result. And if this is vector u, and over here is vector v, thumb is going to show. That's right-hand rule. To find direction of vector c, up or down, okay? Well, we have a little bit more about cross product to discuss. Let me move to the next page. We're going to discuss length of the cross product. Of the cross product. Well, we do guys remember that for dot product, we have a formula for dot product. A formula that dot product between vectors u and v equals length of vector u by length of vector v by cosine of the angle between these two vectors. If you have vector u here and vector v here and the angle here, theta. Well, we are going to have a similar formula for cross product. But because cross product is not a number, dot product is a number. So here is a number, length, and cosine, it's product of three numbers. So it's going to give us a number. Cross product is a vector. So we are going to, instead of using cross product itself, we are going to use a length of cross product. Length of cross product, it's like how long is the resulting vector, c. And this length of cross product is equal to a similar product. Length of vector u, length of vector v, but instead of cosine, we are going to have a sine of the angle between them. Well, kind of symmetrical. I'm not proving this formula, but kind of good, nice formula to maybe remember. So what we have over here, guys, inside we have a vector, but when you take the length, it's going to be a number. Length of the vector is a number. So I keep drawing extra stuff on my board. Okay, so, well, nice formula. Why don't we try to calculate something like maybe length of something or kind of use. So, example, I'm going to calculate length of cross product u and v. Well, guys, we already kind of know one cross product, right, between vectors 1, 2, 3, and I'm going to write down vector 1, 2, 3, and vector v is 4, 5, 6, right? We already calculated cross product between them, and it was -3, 6, -3. What is going to be the length of it? Well, remember, it's a square root, -3 squared, plus 6 squared, plus another -3 squared, which is going to be what? It's going to be 9 plus 36 plus another 9, which is going to be a square root of 54. Okay, so we just calculated the kind of length of cross product. How it can be useful actually? Well, guys, if you look at this formula, we actually can use the length or this number to calculate the angle, right? What I'm going to do, I'm going to calculate sine of theta, which is going to be length of cross product, divided by length of vector u and length of vector v. I already know there's a top. It's a square root of 54. Do I know the bottom? Well, I kind of know it, but I'm going to calculate it one more time. Length of vector u is 1, 2, and 3 squared and added. Length of vector v is 4 and 5 and 6 squared added. And I already know that it's going to be square root of 13 and square root of 77. So I can find the angle between two vectors u and v by a different way, by using the cross product instead of dot product, right? I can say that theta is equal sine inverse of square root of 54 over square root of 14 and 77. And I'm going to calculate that this number, put it in calculator, take sine inverse and calculate that it equals 12.9 degrees. Is it this number going to agree with the cosine way to calculate this angle? Let's check it. Check if cosine way gives the same answer. Okay, cosine is going to be what? The dot product of u and v divided by the length of u and the length of v. Well, we know already the dot product between these two numbers, right? It was 32, but we can multiply it one more time. It's 1 by 4 plus 2 by 3, by 5, sorry. And 3 by 6. And denominator, we already calculated length of u and length of v. It's 14 and 77. So what we have in numerator? 10, 18, which is going to be 28, plus 4, 32. Over square root of 14 by 77. Now we can take a cosine inverse of this 32 over square root of 14 by 77. And I did it on my calculator and I'm getting exactly same answer, 12.9 degrees. You probably will ask me, which way should we use if we do know two vectors? Which way is easier to use and find the angle? Well, you see how much calculations we have if we use the cross product. First, you will need to do the determinant, then find the length. For dot product, it's much easier, right? The top is going to be just at the product of the coordinates. So this way is easier. Easier, sorry, to find the angle. Okay, wrong. Let me way of cosine. So if you are planning to calculate angle between two vectors, use the cosine. Okay. Why do we need the sine then? How do we use a sine? Well, sine is used to calculate one interesting thing. I'm going to change the page and show you one good formula. I don't think that you will use it until you go to multivariable calculus, but it's a nice formula. Maybe eventually you're going to recall that you learned this formula before. Let me write down the cross product formula again. So if you have two vectors across the length of cross product of two vectors, it's a length of vector u by length of vector v by the sine of the angle between these two vectors. I'm going to do vector u over here, vector v over here, and that's an angle. Now guess what I'm going to do? I'm going to draw a triangle using these two vectors. Let me use a different color. I'm going to connect these terminal points and I'm going to have a triangle. What is area of this triangle? Remember the formula is 1 over 2, the side, which is length of vector v, another side, which is length of vector u, and the sine of the angle between these two sides, right? If you compare it to the cross product length, it's exactly the same. The only difference is 1/2. So you can write down that's 1/2 of the length of the cross product. And that's going to be the new formula for area. So you want to find the area of the triangle, you take a cross product, find the length, and do 1/2. When it works, it works when you do have vectors. If you do have just sides, like side here equals 2, side here equals 5, and the angle equals 30 degrees, well, you just use a standard formula, that's numbers. Like standard formula is like A by B by sine of theta by 1/2. If somebody gives you sides, use this formula. If somebody gives you vectors, use this formula. Okay. I think I can calculate, because we already calculated everything for my special vectors 1, 2, 3, and 4, 5, 6. I can calculate the area of the triangle. So in my case, what is going to be the area? Well, I already know that this length is a square root of 54. So that's going to be the area actually, right? Because I calculated the length already, I'm just using it. Okay, do you need to memorize this formula? No, guys, I don't think that you will use it very, very soon. So just kind of, well, maybe do one homework problem on it. Just be aware that formula like this exists. From this section, I want you to remember how to calculate the cross product using the determinant. And I want you to remember that cross product is perpendicular to both vectors. And if you switch the vectors, the cross product is going to change the sign. So 3 major facts. I'm going to write it down. 1, how to calculate determinant. Second, perpendicular to both vectors. So all other formulas you can forget. And number 3, switch vectors, change the sign. Let's write it down like this. Switch vectors, change the sign. Okay, if you do remember these 3 facts, I think it's going to be enough for like nearest future. And for further future, you are going to eventually learn the like better way to find it. Okay. No, that's not the way to write down switch. Okay. Switch vector. So change the sign. Okay, good. Okay, guys, that's all about cross product. And just do the homework. I assigned a few problems over there. Okay. And well, see you in the next lecture.